This is it, the last chapter. We're going to talk now about trigonometry, and specifically trigonometry of right triangles. Once you get into higher levels, you might do some more trigonometry. Non-right triangles, actually, I don't think so. Not in the -3 stream. So we'll take a look at trigonometry, and hopefully you'll get a grasp on it. There is more chances in 20-3 and 30-3 grasp it. If you don't, if you do, those levels in the next couple of courses are going to be great for you because you'll totally get what's going on. All right, so trigonometry of right triangles. We're looking at right triangles. Altitude is one thing that gives us a direct line from the horizon to a vertical line, and sometimes we can figure out an x in here. I'm not going to show you how yet because we're going to go through the specific lesson. You can also figure out how tall things are based on angles and how far away from lighthouses you are if you know the angles. There's all kinds of stuff that uses trigonometry in the world and has been used for hundreds of years. Okay, so working with triangles. Remember, when we are talking about triangles, we label each vertex with an uppercase letter. Each vertex, that's a corner. RST, capital R, capital S, capital T. This triangle will be triangle RST. Each side is then labeled with a lowercase letter that corresponds to the opposite angle. So S, uppercase S, the angle, would be matched by a lowercase s side. Uppercase T would have a side opposite it of lowercase t, and uppercase R would have a side opposite it of lowercase r. So this is how we label. It's really important to know this so that you can understand the formula we're using for trigonometry. Okay, so first super basic question. I just showed you how to do this. Why don't you try doing it before I do it? Make sure you get the answers right, so just pause. There we go. Label each side of the triangles below using a single lowercase letter corresponding to the opposite vertex. So capital X, lowercase x. I do mine kind of squiggly so that you can tell them apart from times symbols. Capital Y, lowercase y. Capital Z, lowercase z. And I do that little line through it so it doesn't look like a 2. And so that's the simplicity of labeling. Some people forget to do it or they don't quite catch on to it. The reverse can also be done. If you have each side labeled, then we can label the vertices, each vertex. So C and C, B and capital B, lowercase a, capital A. Remember, vertices always in uppercase, sides always in lowercase. Okay, so using the Pythagorean Theorem is going to be important to some parts of trigonometry. Trigonometry being the study of triangles. And so you should remember this from junior high. We've got an example on page 291 or some directions on 291. Remember, a triangle, a right triangle, is a triangle with one right angle. So here it's at vertex C. The hypotenuse is always directly across from that right angle. So this is your hypotenuse. It's always also the longest side in your triangle. We call the other two triangles, or the other two sides of the triangle, legs. Pythagorean theorem says that in a right triangle, the sum of the square of the lengths of the legs is equal to the square of the length of the hypotenuse. So the hypotenuse is this one. If you square it, so you multiply it by itself, that's going to give you this side. This is the times C. And then A and B, I should probably label this. This is A, this is B, this is C. A squared plus B squared. So A times A plus B times B equals C times C. We need right triangles for the Pythagorean theorem to work. It has to be a right angle triangle, otherwise you don't technically have a hypotenuse. This is the only type of triangle that this works with. It's not a right triangle, can't do it. Do not use it. Not all triangles are going to be labeled ABC properly. They won't always be in that order. You have to understand how to use the formula. So when you're using this formula, this C is always the hypotenuse. The one by itself is always the hypotenuse. Okay, so label the sides of a triangle and state the Pythagorean theorem as it applies to it. Well, this is capital P, so this is lowercase. Capital Q, lowercase q. Capital R, lowercase r. Now, the Pythagorean theorem is a squared plus b squared equals c squared. Sorry, yeah, those shouldn't be capital, should they? They should be lowercase because we're talking about side lengths. A squared plus b squared equals c squared. But that's not our triangle. In this case, our triangle is PQ and R. Q is the hypotenuse. So we're going to put Q by itself on one side, squared, and then b squared plus r squared equals q squared. Make sense? Hopefully. Okay, let's actually try it out with several side lengths. So create a triangle with a leg that is 3 colored squares long. Then create leg B, which is 4 colored squared longs. How many colored squares long is a hypotenuse? Okay, well, how do we do that? We have to use squares as we have here. All right, as you can see, I've drawn a triangle that is 3 squares long. It is 4 squares high, and we have a hypotenuse here. Now, how do we tell how many squares long that is? Well, if we could cut it out, we could lay it along here. The other thing I can do is I can use a rotation button. And so what I'm going to do is I'm going to rotate this until it is horizontal. And lo and behold, you can see it is 5 squares across. It's not exactly the way it's shown, but it's pretty darn close. Let's take a look back at our question. So what should it be according to the Pythagorean theorem? So if we square each leg, if this is 3 and this is 4, and we discovered that the hypotenuse was 5. 3 squared equals 9. 4 squared equals 16. And 5 squared equals 25. Does a squared plus b squared equal c squared? Is 9 plus 16 equal to 25? Yeah, it is. So we can see here with a simple triangle, 3 side lengths of 3 and 4, or leg lengths of 3 and 4, and hypotenuse of length 5, the Pythagorean theorem holds. And it will hold for any triangle. Trust me on that one, I'm not going to prove it at night. Given the following diagram, use the lettering provided to state 3 Pythagorean theorem relations that apply. So, to take these Pythagorean relations, what we want to do is we want to take a look at our side lengths. So we have 3 different triangles we can consider, actually. We can take a look at triangle ABC. We can take a look at triangle BCD, or we can take a look at triangle ABD. So we kind of have 3 different triangles in there. We can state our 3 Pythagorean relationships. If we are looking at the blue triangle I've labeled here, the one side length we don't have on there is B. We could call it x plus y, or we could call it B. Again, this example, as you can see, is on page 292. So we can state our Pythagorean relationship for the blue triangle. Our hypotenuse is B. So it's going to be by itself on one side, which means that A squared plus C squared, our two leg lengths, are going to equal to B squared. Let's take a look at our green triangle, which is AZ and Y are our three lengths. So the hypotenuse of this one is the one away from the right angle. That means it's A, that's the longest one in here. So A is going to be by itself in this. And then we know that Z squared plus Y squared is equal to A squared. And finally, with our red triangle, we have CX and Z as our side lengths. C in this case is our hypotenuse, so it goes by itself on one side. And we get X squared plus Z squared equals C squared. And that's three Pythagorean relations. Pythagorean relationship is just this formula. Okay, next. Rearrange the Pythagorean theorem to solve first for X and then for Y. So if we want to solve for X, that means we need to get it by itself. I've seen a few people having trouble with this on the quizzes. So in order to solve for something, you got to take away things that are on the same side as it, other terms that are on the same side of it first. So this is a term, this is a term, this is a term. We remove a term by doing the opposite operation. These two terms are added together, so if we subtract y squared from this side, we're going to get 0. What we do to one side in an equation when we're rearranging it, we must do to the other side. We're going to subtract y from this side as well. Subtract y squared from both sides, we have x squared equals z squared minus y squared. Well, that's great, but we want to solve for x. We want to get this guy all by himself, but he's got this little 2 up top, this little square, meaning it's x times x. We do the same thing at each step. We're going to do an opposite operation to try to get this guy alone. And the opposite of a squaring operation is a square root operation. So if we can take the square root of x squared, we're going to get x. At the same time as we do the square root on this side, though, we have to do it on this side to keep both sides of the equation true. So we take the square root of this, and we get x equals the square root of z squared minus y squared. Now, really important, you can't do the square root of z squared minus the square root of y squared, because we know the square root of z squared equals z and the square root of y squared equals y, and that would just be x equals z minus y. That's not the Pythagorean relationship. We've got squares in here. They're important. So we have to do what's inside the square root symbol before we can apply the square root. Especially if you're using the calculator on your phone, it's important to do this in the right order. You must follow BEDMAS. So first, you're going to multiply z by z, and you're going to multiply y by y. You're going to subtract that from this, hit your equals, and then take a square root of the whole thing. So that's solving for x. If we want to solve for y, then starting from the same place, x squared plus y squared equals z squared. Then we're going to just simply subtract x from both sides. We want to get y squared by itself. Now we get y squared equals z squared minus x squared. And y equals the square root of z squared minus x squared. If we just wanted to solve for x, or for z rather, we just have to go straight into taking the square root of both sides. So what do you notice about the Pythagorean relationship? When you're solving for a side, you're always going to be doing a square root of a sum or a difference. If you're solving for the hypotenuse, you're going to be adding. If you're solving for one of the legs, the leg is going to be smaller than the hypotenuse when you solve it. So you're actually going to be doing a subtraction underneath that square root sign. That can be helpful to remember, to make sure. And then when you get to your final answer, make sure that your final answer has the legs as each smaller than the hypotenuse. I think we got one example of this with numbers to actually figure this out. And then, oh, we got a couple of more examples. Let's look at this one first. Okay, so use the Pythagorean relation to find the length of the missing sides of the triangle to the nearest tenth of a unit. We've got triangle PQR and a Pythagorean theorem that uses different letters. So let's start by rewriting that with PQ and R. Q is the hypotenuse, so it has to be by itself. And this is going to be R squared plus P squared. And when we solve for Q, we get Q equals the square root of R squared plus P squared. I guess we might as well put those numbers in, right? What's R? It's 3.8. And P is 5.2. And I'm going to do this step by step just to show you what's going on, in case you want to do this on your phone and you don't want to get things in the wrong order. It is always a good idea. Okay. Calculator. 3.8. Whoop, just lost my calculator for some reason. 3.8 times 3.8. That's what 3.8 squared means, of course. 14.44. 5.2 times 5.2 is 27.04. So then we add those together. So we're looking for the square root of 41.48 equals Q. And we need to use the square root button for that. Clear. 41.48 square rooted. Well, mine actually does it in order, so I got to hit my square root first. 41.48 square rooted is 6.44, but we're going to round that down. So 6.4, and our units should be meters. It is important, though not something we actually go into, that these units are the same as each other in order to do this. You can't do it with different units, but I don't think if we ever throw a question at you that has different units. So be aware of that in the real world. They should be the same units. 6.4 meters is Q. So we put that back up here. And our final check, again, should always be, does this size of hypotenuse make sense? Your hypotenuse will always be the largest of your three side lengths. And it will always also be smaller than those two added together. It'll be smaller than these two added together. And if you are confused about that or wondering about that, try putting 3 different sticks into a triangle. And see if you can do it. Put them into a right triangle with a hypotenuse that is longer than the other two added together. Hint, you can't. All right, one last one. If a field is 120 by 180, how much shorter is your route if you walk diagonally across the field rather than walking around the edge, the opposite corner? I don't know if I just liked trig too much when I was in high school, or what. Like, I feel like I try to do the lazy thing and walk as little as possible in terms of distance. So I'll cut corners whenever I'm out walking. Well, as long as I'm not going to ruin the grass by doing so. But sometimes I do this in the snow. There's like these giant snow hills and barriers and obstacles to overcome. So instead of just walking around, I'll try going over, but it's probably a lot more work to do it that way. Anyway, let's do the math related here. So 120 by 180. So 180 would be the longer dimension. 120 would be the shorter dimension. And we want to know how much the diagonal is. We can use Pythagorean theorem for this. If this is going to be our hypotenuse, right? Sorry, that shouldn't be squared yet. Pythagorean theorem says that c squared equals 120 squared plus 180 squared. Notice that a diagonal is a right-angled triangle. We've got a right angle formed here, or you can use the top half as well. And so we can do the calculations here. Square root of 120 squared plus 180 squared. Close my brackets. And so all of that will have to be in brackets. So you want to do square root of brackets 120 squared plus 180 squared. If you're using a phone, right? You're going to have brackets around this whole thing in here as well. Okay, because these happen first, and then this happens, and then this happens. So make sure your calculator is doing it that way. If you're not sure. And then once you get your answer, check it. So I get an answer equals 216.3 meters. 216.3 meters. Is that my answer? Is it 216 meters shorter to walk diagonally across the field? No, that's how far it is to walk across the field. So how much shorter is it? Well, if you don't walk across the field, it's 180 plus 120 meters. If you do walk across the field, it's 216 meters. So we subtract that to find out that it is 83.7 meters shorter. So you saved yourself a lot of walking. Great. Good job, you. That's it for lesson 1 of trigonometry, just the Pythagorean theorem. Next, we're going to get into the fun trig ratios. And this is the part that I really enjoy. Pythagorean theorem, a lot of square roots and squares and stuff, and it's a lot more work, I find, than the rest of trig. Once you get the handle of the rest of trig, you'll probably really quite enjoy it. Okay, thanks. See you next time.